Last week, the US Senate had a hearing on the dangers of social media in preparation of a legislation to improve child safety online. In this hearing, Meta CEO Mark Zuckerberg claimed that it has not been scientifically proven that social media causes mental health problems in adolescents.
Mr. Zuckerberg, let me start with you. Did I hear you say in your opening statement that there's no link between mental health and social media use?
Senator, what I said is I think it's important to look at the science. I know people widely talk about this as if that is something that's already been proven. And I think that the bulk of the scientific evidence does not support that.
This upset a lot of people who think that the link is obvious. But I'm afraid Zuckerberg is right. Let's have a look. Contrary to what some headlines have claimed, we don't have a global mental health crisis. I discussed this at length in an earlier episode. By and large, mental health globally has been remarkably stable. However, the mental health of one demographic group has been suffering in the past decade, and that's adolescent girls in some countries and to a lesser extent also boys. This is evident in data from the USA, the UK, Australia, New Zealand and some other countries where self-reports also correlate with self-harm. In other countries, such as Sweden, this mental health trend is primarily found in self-reports from girls, difficult to interpret, and does not correlate with self-harm statistics. Still, many put the blame on the increased use of social media, and that includes the affected young people themselves. It's a topic I care a lot about because I have 2 children who just got their first smartphones. The most vocal critic of social media use for children has probably been the American psychologist Jonathan Haidt. His major argument is that there isn't any other hypothesis, which is also what string theorists said about the existence of strings and generally not how science works. Now, look, I'm not saying that Haidt is wrong. I don't know what's going on, but I do know that the studies on the topic have been inconclusive. I don't expect you to believe what I say, but Haidt has been criticized by his own colleagues for jumping to conclusions. And again, it's not that they say he's wrong. They point out that to the extent that studies have found any influence of social media on young people's mental health, it's been a small effect. For example, a study from 2019 followed about 13,000 adolescents in the UK between the ages of 10 and 15, though not all of them participated in all parts of the study. They were asked how many hours a day they were interacting with friends through social media and to rate their well-being, but they were also asked about their life at home. The correlation between social media use and life satisfaction was very small and in many cases almost compatible with 0. A similar conclusion was reached in 2020 by a group of researchers who followed a group of 500 adolescents in the United States for 8 years from age 13 to 20. They found that more time spent on social media was not associated with more mental health issues. The authors conclude basically that research should move on. However, then there's this study from 2022 by researchers from the UK and the Netherlands. They looked at the mental health of over 20,000 kids in the UK in the age range of 10 to 15. They found that for girls between the ages of 10 and 13, increases in social media use predicted a decrease in life satisfaction ratings 1 year later. Something similar happened to boys, but at ages 14 and 15. So this seems to show that there is both an effect and the causation indeed goes from social media use to decreases in life satisfaction and not the other way round. Then again, there's a recent study by researchers from the UK published in the journal Nature Mental Health. These researchers followed over 12,000 British teenagers. They found that while social media does have a negative impact on mental health, it's one of the least influential factors. The authors say that it makes no sense to act as if social media use is such a big reason for adolescent mental health problems, and that other factors such as bullying or lack of family support should be the focus of attention instead. Quite possibly, the reason is similar to the issue with the supposed problem of political polarization and echo chambers, which Jonathan Haidt has also previously been going on about, and that I discussed at length in yet another episode. Upon closer inspection, it turns out that while these problems of polarization and echo chambers do exist, their strength and prevalence depends on the medium and the country and on exactly what question you ask. Basically, the issue is that psychology and sociology are very context dependent. Not every field of science is as nice as physics, where you have universal laws and Einstein's whose theories still hold up a century later. My reading of the literature on the subject of social media and mental health is that some psychologists are a little wary and worry that blaming social media for whatever problems children have might paper over other issues. And just so we're on the same page, it's not like I'm saying social media is no problem for children or anyone really, or that the law which the Senate is working on isn't needed. Actually, much of the Senate hearing focused on other issues, such as privacy concerns or children being able to buy products they shouldn't get their hands on, or being exposed to content that's unsuitable for their age, such as deep existential problems posed by quantum mechanics. It's a wild world out there, so stay safe. I got a lot of questions last week about an article in Quantum magazine about dark dimensions. And for a change, this is a case where I think I'm actually the right person to ask. What's this all about? Let's have a look. This recent work is based on string theory, an approach to a theory of everything that was invented in the 1970s. It was quite popular in the 80s and 90s. One of its main features is that it requires 9 dimensions of space. Now, as you've probably noticed, we don't live in 9 dimensions. So string theorists assume that 6 of these dimensions are not infinitely large. They're rolled up to such small sizes that we wouldn't notice them. The new paper says that the extra dimensions could explain dark matter, if that exists, which it may not. Hence the combination dark dimensions. Dark matter is what astrophysicists think makes up 80% of all matter in the universe, but we can't see it, and we have never managed to directly detect it. We only indirectly infer the presence of dark matter from its gravitational pull. This is why there's an alternative idea that there's no dark matter. It's that we've got the law of gravity wrong, though Albert doesn't like that at all. But back to the extra dimensions. In the original idea of string theory, these additional dimensions were so small that we can't measure them at all, about 10 to the minus 35 meters, a size known as the Planck length. It's named after Max Planck, who also made the quip that science progresses one funeral at a time, though I think that was very optimistic. Then, in the late 1990s, some people had the ingenious idea to just conjecture that one or several of these hypothetical dimensions are much larger than the Planck length, so that they could become measurable with the next generations of experiments. These were called the large extra dimensions. You see, the way this kind of research works is that it's always the next experiment that'll test these ideas. And if that next experiment doesn't find the stuff, then it's the next after that, and so on. Physicists usually justify this by a pseudoscientific argument called naturalness, according to which some otherwise arbitrary values of model parameters are preferred by nature. These naturalness predictions can be shifted because they're not scientific to begin with. 20 years ago, there were a number of experiments that looked for these large extra dimensions, particle colliders, astrophysics, tabletop, and so on, and would you believe it? They didn't find them. The new paper is now about a revival of this old idea of large extra dimensions. Indeed, these dark dimensions are a new research program that seems to have begun in 2022 around Kumrun Waffa, a string theorist at Harvard who has been doing this stuff for decades. In their scenario, there's one extra dimension that is particularly large, and they ignore the other 5 as being too small to be measurable. This is not new. It was a rather common setup 20 years ago. The new thing is the justification for why this one dimension has a size of about 1 micrometer. This is supposedly natural because it's related to the cosmological constant and something with the swampland. Doesn't really matter exactly what this means because the swampland isn't real and naturalness arguments have failed over and over again in the past. In any case, this supposedly natural size of the extra dimension is great because, guess what? It could be tested with one of the next experiments. The current experimental constraints on the size of this dimension is currently about 52 micrometers. Okay, but what does this have to do with dark matter? Well, in such large extra dimensions, you must assume that forces which we have measured on very short distances, that's the nuclear forces and also electromagnetism, don't notice the additional dimensions. And actually, all the matter that we are made of can't travel into these directions either. In string theory speech, the normal matter is confined to the brain. That's BRANE, not BRIAN, is derived from membrane and is our normal three-dimensional space. So all the normal stuff needs to stay on that three-dimensional brain. The reason is that atomic nuclei are much smaller than this micrometer, which is the supposed size of the extra dimension. And if the constituents of nuclei could spread into more than 3 dimensions, nuclear physics wouldn't properly work. But here's the thing. There's no such problem for gravity, so they can assume that gravity does experience the large extra dimensions. And these extra dimensions then explain dark matter as follows. Whenever you have rolled something up, you get standing waves in this rolled up direction. For gravity, these standing waves are quanta of the gravitational field called gravitons. And if they are standing waves, they have masses that depend on how many wavelengths fit into the extra dimension. These massive gravitons can make up dark matter. Again, this isn't a new idea. This is the same thing people did 25 years ago. They were even looking for this stuff at the LHC and didn't find it. For this new theory, they just use some parameter ranges that have not yet been excluded. The novelty of the dark dimension scenario is now that the extra dimension doesn't have the same radius everywhere. This has the effect that the mass of these gravitons isn't the same everywhere, and the heavier ones can decay into lighter ones. This basically heats up the gravitons with lower masses, and since they're hotter, that changes the behavior of the dark stuff. They say that this heating effect would affect the large-scale structure of galactic filaments, and guess what? That future experiments could soon rule that out. You know what? I'll go out on a limb and say they won't find any evidence for the decay of these massive gravitons. Electric vehicles are great, but let's be honest, it's more convenient to fill up a fuel tank with gasoline than sit around and wait until the battery is full. It takes so long that sometimes you even have to talk to other people at the charging place. Well, this new battery from researchers at Cornell might solve the problem. Let's have a look. Lithium batteries, or any batteries, really have two poles, plus and minus, called the anode and cathode. When you use the battery, negatively charged ions will move from the minus to the plus side through a substrate called an electrolyte. This movement of charges creates a current that powers your device. When you recharge the battery, these particles have to move back from the plus to the minus side so that you can use it again. So the battery has these 3 main ingredients: the anode, the cathode, and the electrolyte. And since all good things come in threes, for a good battery you need a mix of materials with 3 properties. First, you need something that can reliably and durably store charges. That is, the battery needs a low self-discharge rate. It must also be possible to repeat the process of using and recharging the battery repeatedly. That is, you want a long life cycle. And third, you also want something that can store a lot of charge in a small place, that is a high energy density. Lithium-ion batteries score high on all 3 counts, which is why they have become so widely used. In a lithium-ion battery, the cathode contains lithium, hence the name. The anode is usually graphite, though there is some variety in materials. Currently, the fastest charging lithium batteries for electric vehicles can go from 20 to 80% in about 15 to 20 minutes. However, these extra fast charging batteries are more expensive than the usual ones, which take 2 or 3 times as long. Of course, it's not just electric vehicles, but pretty much any other mobile device that's now powered by lithium batteries. Phone, tablets, cameras. My new phone, that's a Samsung S24, takes about 60 to 90 minutes to fully charge. No, it's not the Ultra version. Does anyone really need a terabyte of storage? Do you? For what? The new research now comes from Cornell University and was just published. It's an experimental work in which they test a new type of battery. They used a combination of lithium and indium in the battery anode. Usually, the anode is made of graphite. Indium is element 49 of the periodic table. It's a metal, and the reason it's called indium is because it has a spectral line that is indigo blue. It has 2 important properties that made the researchers think it'd be good for the task. First, indium has what's called a low migration energy barrier. This isn't a political statement about economic refugees. It means that the ions have a small energy barrier to overcome when one charges the battery. Basically, they move easily. And second, indium has a small exchange current density, which means it can store energy for a long time. In their tests, the researchers were able to charge the battery in about 2 minutes and show stability in over 1,000 cycles. Now, this sounds quite promising, but there are a lot of ifs and buts. First of all, they quote an energy density of 145 watt-hours per kilogram, which isn't bad, but about half of that of current lithium-ion batteries. Then there's the question how robust such a battery is and how well it copes with different temperatures. There's also the issue that indium is at the moment mostly produced as a byproduct of zinc mining. It'd probably be difficult to rapidly increase its supply because there's very little direct production. And then there is the question whether it even matters how fast the thing charges. Because I believe what people with range anxiety are worried about is not so much that it'll take a long time to charge an electric vehicle. It's that they must stop and charge it to begin with. If I had a choice between a lithium-ion battery that takes an hour to charge and one that's twice as large but charges in 5 minutes, I'd stick with the lithium battery. I can't really think of any situation where I need to charge a phone in 5 minutes. What do you think? Let me know in the comments. Nuclear fusion is a great idea in principle. In principle, it could solve the energy worries of the world beautifully. The problem is that whenever we've tried, getting nuclear fusion to work takes up more energy than it creates. But a team from Japan and the United States just got us a bit closer to our dream of a perfectly clean source of energy. They recently succeeded in controlling nuclear plasma in a stellarator by creating a digital twin. What's a stellarator? What's a digital twin? And what did they actually do? Let's have a look. It used to be that there was basically only one approach to nuclear fusion, that was a tokamak. A tokamak is a donut-shaped device in which the hot nuclear fuel is held and heated with magnetic fields until the nuclei start fusing. The existing tokamaks are huge. For example, the one at ITER will be contained in a 70 meters high building. That's about 20 floors. But in the past decade, we have seen a lot of nuclear fusion startups that pursue different ideas. Yes, most of them use tokamaks, but some of them use what's called a stellarator, which is what they used for this new work. A stellarator is still a donut shape, but it has a more complicated magnetic field that allows the device to be smaller and should also make it harder for the plasma to escape, thereby increasing efficiency. The biggest existing one is Wendelstein 7X in Greifswald, Germany. The problem is these stellarators are much more difficult to build than tokamaks, and they're also more difficult to model, so they haven't been studied all that much. Some companies use entirely different approaches. Notably, there's what's called inertial confinement. Inertial confinement basically means you shoot at a fuel pellet in the hope that it blows up and then use the energy. You can shoot at it either with lasers, that's what they do at the National Ignition Facility in the United States, or you can do it with a kind of bullet in what's basically a big gun. That's what they do, for example, at the startup First Light Fusion, where they've called their device Big Friendly Gun. Yes, I can see it smiling, very friendly. And there are a few other startup ideas such as the Z-pinch. I covered all of this in a long episode last year. But let's come back to the new paper. The major issue with both standard tokamaks and stellarators is that it's difficult to control the plasma in these devices. The motion is chaotic, which makes it a pain to steer. And if the plasma gets out of control, it can damage the reactor vessel. Because of this, when it looks like the plasma is becoming unstable, the process of heating and fusing must be quickly aborted. This is the biggest problem for making this approach to nuclear fusion energy efficient. But this is an area where computing power can make a big difference through a method that's called chaos control. For example, already in 2019, a group of researchers from Harvard and Princeton trained an artificially intelligent system on data from the Joint European Torus that's currently the largest tokamak in the world, and another tokamak that's currently the biggest in the United States. They taught it to recognize data patterns that signal an impending plasma instability. This was a hindsight analysis on data that had previously been collected, but they correctly identified an imminent instability 1 second ahead in somewhat more than 80% of cases, and 30 milliseconds ahead, they saw almost all instabilities coming. You then want to do this in real time, and indeed this was done last year by researchers from DeepMind. They actively controlled plasma in a tokamak device called TCV, located at the Swiss Plasma Center in Lausanne. It's a fairly small reactor with a size of just about 2 meters in each direction. In it, the plasma is held by strong magnetic fields that can be manipulated with a number of controllers. To make this work, the people from DeepMind first trained their artificial intelligence on a tokamak simulator that has also been developed by the group in Lausanne. So take the AI, train it to control another software to save time, and then take the trained AI to control the real thing. And their AI control of the plasma worked out beautifully. In this movie, on the left, you see the measurement of the actual plasma inside the tokamak. On the right, you see the reconstructed shape of the plasma. The DeepMind people were able to coax the plasma into a large number of different shapes, including a triangular one and 2 separate droplets. This then brings me to the new paper, which did a similar thing to what the DeepMind people did last year, but with a new method on a different device. This was done by a team of researchers from Japan and the United States at the Large Helical Device in Japan. This is a stellarator, the second largest in the world after Wendelstein X. They used a new method for controlling fusion plasma by using a digital twin. That's a virtual replica of the plasma created on a computer, though I think digital twin is just a buzzword for model. One then uses real-time observations to update the twin and try to predict what happens next to control the plasma in return. The process is called data assimilation, and it has more physics built in than the AI-based approach used by DeepMind. In particular, they used what's known as ensemble forecasting, in which you assume some amount of uncertainty for the exact current state of the system and make a prediction for a set of initial values. Then you calculate the most likely one. It's the same method that's also used for making a weather forecast. In this experiment, they controlled the temperature in the center of the plasma, and you can see here that their control method nicely reached the target they aimed at. However, neither this nor the previous experiment by DeepMind actually controlled an ongoing fusion process. They just steered the plasma without fusion. Clearly, actively controlling the fusion process will be next, and I'll let you know when that happens, so stay tuned. You don't want to miss the world revolution, do you? We've seen a few new headlines this week about the plans of particle physicists to build a huge new collider at CERN in Geneva. I've had a look. Particle physicists have called their new dream machine the Future Circular Collider, FCC for short. The FCC is supposed to be a ring collider like the Large Hadron Collider, which is currently the biggest collider in the world. The LHC primarily collides protons, has a circumference of about 27 kilometers and reaches a collision energy of up to 14 tera-electron-volt. When we first heard of CERN's plans about 5 years ago, the circumference of the new collider was projected at 100 kilometers with a target energy of 100 tera-electron-volt. CERN then began commissioning more detailed plans and reports, and the circumference has now been updated to merely 91 kilometers. It has also emerged that the tunnel will be deeper underground, on average 200 meters rather than about 80 meters like the LHC, probably due to geological features, and that the tunnel cross-section will be approximately 5.5 meters. CERN's plan is to run the FCC project in 2 stages. The first stage is called the FCC-EE and would collide electrons. This stage would not reach any record energy, but just roughly 400 GeV. This is actually lower than the energy that the LHC currently reaches. However, the LHC collides protons, which are composite particles made of 3 quarks. Electrons, on the other hand, are fundamental and not made up of anything. But the LHC collides composite particles, introduces some additional uncertainty and spreads out the energy in each collision over the constituents. An electron collider like the FCC-EE therefore can deliver better data even at lower energy. The primary goals of this first stage would be to produce a lot of Higgs bosons. The Higgs boson was the last fundamental particle to be discovered at the LHC in 2012. It's still the new kid in town and hasn't been studied as much as the other particles, so naturally particle physicists want to have a closer look. If CERN can get the money together, which to my best knowledge has not yet happened, then constructions for the FCC-EE could begin within 5 years and it could start operating in the mid-2040s. The second stage would be the FCC-HH, where H stands for hadron. It would then collide both protons and heavy ions like the LHC. The projected construction cost for both stages is around 20 billion euro or so. That does not include the operation costs, which is probably something around $1 billion a year. The BBC article quotes a cost of 12 billion, presumably for the first stage of the project. CERN will probably need some contributions from international partners to pull that off. Why spend that amount of money? According to the BBC, the purpose of the bigger collider is to figure out what dark energy and dark matter is made of, as you can see in the title. The BBC didn't invent that themselves. They got it from none other than CERN's Director General, Fabiola Gianotti. She's quoted saying that the FCC is needed because the discovery of these dark particles would lead to a new, more complete theory of how the universe works. Now, it's true that a discovery of dark particles, if they exist, would lead to a more complete theory of how the universe works, but there's no reason to think that the FCC will be of any help in that. I find it honestly painful that CERN physicists still try to mislead the public about the prospects of their experiments. Let me remind you that they also told you that the LHC would find dark matter, which it did not, and indeed it was never likely that it would. Now, the first time they did this, I was willing to believe that they were themselves confused, but now I'm no longer willing to accept this as an excuse. At this point, it's deliberate misinformation. Now, look, it's not that I'm against particle physics or something. Some of my best friends are Higgs bosons. I understand just fine that particle physicists want to measure a few more constants a little bit more precisely. But that's not a good selling point, is it? The smarter among the particle physicists have recently tried to convince people that it's somehow interesting to study the self-coupling of the Higgs boson. But that didn't quite catch on. Maybe not so surprisingly, because besides particle physicists, no one gives a damn about it. Interestingly enough, American particle physicists seem to have noticed that the tide is turning, and they're instead rallying for muon collider, I talked about this in an earlier episode, that it almost certainly be less expensive and is also easier to sell because we've never had a muon collider before. Even if the thing doesn't find anything, it has this novelty sticker going for it. But I think particle physicists need to wake up. They seem to believe they're entitled to dozens of billions of dollars in return for nothing in particular, while the world is going to hell in a handbasket. For what I'm concerned, this future collider should remain a future collider. Some people have called me a doomer. Others call me a pessimist. Personally, I think I'm a realist. If I look at the plans that most nations have made to limit their contributions to climate change, I think it's just not going to happen. The people making these plans are either ill-informed, delusional, or lying, or maybe all of the above. Now, there's a new publication just out of the University of Melbourne in Australia that, according to the press release, has revealed a huge climate mitigation challenge and claims that the IPCC has overestimated how much carbon dioxide removal can realistically accomplish. Yes, let's have a look. Okay, I admit I'm partly talking about this because I feel like some people have misunderstood my position on what we should do about climate change. They're probably confused because I've said both that A, we need to get serious about carbon dioxide removal, and B, carbon dioxide removal isn't going to save the day. So how do these two things fit together? Well, they fit together because I'm a doomer. I mean a realist. I'm a realist. Carbon dioxide removal isn't going to help much, but it's going to help a little, and in contrast to the idea that we'll just stop oil, I can see it actually happening. If you're wondering why I have difficulties believing that we'll just stop using fossil fuels, let me tell you a little story from the local neighborhood. A couple of months ago, they drilled a hole about 30 kilometers north of here. They found oil. The company happily reports that the oil is of very high quality, and now they're building a well. Does this look like we're going to stop using fossil fuels? Because it's not what it looks like to me. So, carbon dioxide removal. Not great, but better than nothing. Let's do it. So much about me, but I wanted to talk about this new paper. First, though, I need to sort out a terminology issue because I've noticed that a lot of people confuse carbon dioxide removal, carbon capture and storage, and direct air capture. These are three different things. Carbon dioxide removal is anything that reduces carbon dioxide levels in the atmosphere. Trees, for example, do carbon dioxide removal, but any technology which mimics this process also counts. Carbon capture and storage, in contrast, is a way of partly preventing the emission of carbon dioxide, for example, on power plants, but it doesn't entirely prevent the emission. So if you do it at a fossil fuel plant, that doesn't remove carbon dioxide from the atmosphere, it just reduces the emission. Therefore, carbon capture and storage at fossil fuel plants is not a method of carbon dioxide removal. However, if you do carbon capture and storage when burning biomass, then you actually do reduce the carbon dioxide in the atmosphere because the biomass, such as trees, took the carbon out of the air. This is called bioenergy with carbon capture and storage, BACS for short. It's also a way of producing energy. Yes, you can actually make energy by removing carbon dioxide. And since you can make energy and therefore money with it, this has been the most popular way of removing carbon dioxide. And finally, direct air capture is a different method of carbon dioxide removal. It basically works by pumping air through huge filters and trapping the carbon dioxide. It's highly inefficient because the density of carbon dioxide in the air is quite low, and it also takes up a lot of energy. There are only a few experimental direct air capture installations to date, and there are some other methods of carbon dioxide removal, but the currently most widely used one is BACS. If someone tells you that carbon dioxide removal basically doesn't exist, they're probably confusing carbon dioxide removal with direct air capture. It's clear by now that there's no way we'll limit warming to below 2 degrees without carbon dioxide removal. The International Energy Agency concluded in a report from 2022 that reaching net zero by 2050 is virtually impossible without carbon dioxide dioxide removal. The IPCC too writes very clearly that carbon dioxide removal is part of all modeled scenarios that limit global warming to 2 degrees or lower by 2100. Okay, the thing is now that all plans to get to net zero by 2050 rely on extensive carbon dioxide removal in some way. Given that the currently biggest contributor is bioenergy with carbon capture and storage, a lot of people put their hopes on that. And this then brings me to the new paper. The IPCC draws conclusions by working out what they call mitigation pathways that are basically possible courses of action. The authors of the new paper now say that for what carbon dioxide removal is concerned, those pathways proposed in the IPCC report are not only unrealistic, they're actually problematic. They write that carbon dioxide removal deployments, quote, pose major economic, technological and social feasibility challenges, threaten food security and human rights, and risk overstepping multiple planetary boundaries with potentially irreversible consequences, end quote. As I said, the major method of carbon dioxide removal is currently bioenergy with carbon capture and storage. And the problem is that to scale this up, you need all this bioenergy in the first place. That means in practical terms you need to grow stuff, and growing stuff needs land that other people might want to use for other things. The authors of the new paper looked at the numbers which the IPCC assumes for this technology, and the IPCC projects that BACs could remove up to 10 or 11 billion tons of carbon dioxide per year. The authors then estimate that this will, quote, require converting up to 29 million square kilometers of land, over 3 times the area of the United States, to bioenergy, crops or trees, and potentially push over 300 million people into food insecurity, end quote. They say that a realistic estimate would be more like 2 to 3 billion tons of carbon dioxide per year removed by this method, which is about a quarter of the IPCC estimate. Basically, this means that even the IPCC plans to limit warming to 2 degrees are unrealistic. Though personally, I think one doesn't need a paper published in Science to see this. You just need to know that at the moment the amount of carbon dioxide that we actively remove, mostly by BACs, is a little more than 2 million tons a year. Doesn't look likely that we're going to reach 2 billion anytime soon, does it? Okay, I've seen a lot of weird ideas for what dark matter could be. But this one surprised even me. A team of researchers proposes that the universe might be filled with singularities, and those could make up what we call dark matter. I had a look at the paper. This new paper is about what's called naked singularities. They're called naked not because they're missing panties, that's knickers for the British audience, but because they're missing a horizon like black holes have. A horizon is the boundary of a region from within which light can't escape. It's why we can't see what's inside a black hole. For a black hole, it's like part of space becomes entirely inaccessible. Inside the black hole horizon, there's a singularity. That's a place where matter is crushed by its own gravity until it's infinitely dense. A naked singularity, on the other hand, has a plain view on that singularity. There's no horizon hiding it. Black holes and naked singularities are both solutions of Einstein's theory of general relativity. Yes, it's Albert again. We know that black holes exist, but we don't know whether naked singularities exist. There's a conjecture called the cosmic censorship hypothesis that has it that all singularities in our universe are hidden behind a horizon. But it's never been fully mathematically proved, and it's somewhat controversial whether it's correct and fulfilled in nature. This is because there are computer simulations that strongly suggest naked singularities can indeed form from gravitational collapse. Of course, a computer doesn't actually ever spit out infinity. You just calculate until the number's so large it might as well be infinity. And that's just as well because most physicists don't actually think that singularities are real. They think that, well, most of the time they probably think there's a bug in their code. But if it's not the code when a singularity appears in the mathematics of a theory, not the simulation, they think it means that the theory breaks down and needs to be replaced by something better. And when it comes to infinite energy densities created by gravity, they think what happens is that when the densities get very high and the curvature of space very large, then we need to take into account the quantum properties of space and time. For this, we need a theory of quantum gravity, which we don't have. But that doesn't make naked singularities any less interesting. It makes them more interesting. It's because they'd give us a plain view onto a region with strong quantum gravitational effects. There's no other place where we can find that. This is why I was very interested in naked singularities 10 years ago or so, because I was wondering whether, in case they're there and make gravitational lensing, that could tell us something about quantum gravity. But then someone did the maths, and it turned out that they would be very difficult to tell apart from black holes, so that idea never went anywhere. In any case, this brings me to the new paper. These guys now say that naked singularities, a lot of them, could form in the early universe. This idea isn't totally crazy. You see, in the early universe, all matter's in the form of a hot plasma. The plasma isn't entirely smooth. It's more like my attempt to make hollandaise sauce. In some places, the density is a bit higher. In some places, it's a bit lower. And the places with higher density will go on to contract under the pull of gravity. At least that's what I tell myself about my sauce-making attempts. Normally, we say that the places of higher density go on to form stars and later galaxies. But if the fluctuations are large enough, they can form what's called primordial black holes. And the authors of the new paper now say, well, they could also form primordial naked singularities. The black holes that we observe out there in the cosmos are formed from the collapse of stars or from the accumulation of matter onto those stars. They are extremely massive because there are no other astrophysical processes in the late universe to create them. But primordial black holes could have been created at any mass. In particular, they could be fairly small and now be distributed throughout the universe. This makes primordial black holes possible candidates for dark matter, if that exists, which it may not. However, this idea has meanwhile been mostly discarded because it's in conflict with observations. The reason is that we know how much mass there must be in dark matter in total. It must add up to about 4 times as much as the normal mass. That's a lot. And that's the average over the entire universe. Within galaxies like the Milky Way, you need 10 or 20 times as much mass in dark matter than normal matter. If that's all black holes, where are they? Depending on the mass of the black holes, they'd lead to different observable consequences. They do a lot of gravitational lensing, which we haven't seen. They distort the cosmic microwave background, which we haven't seen. They could go through stars and collapse them, which we haven't seen. The very small ones would evaporate and leave behind flashes of light, which we haven't seen. They could still make a contribution to dark matter, which is why some people are still working on it, but it looks like they don't make up the bulk. In the new paper now, they say that maybe what's happening is that the early universe didn't create primordial black holes, but primordial naked singularities. And while these would look similar for what gravitational lensing is concerned, they might not do much to collapse stars, and so they'd make more viable dark matter candidates. This paper seems to be the first one about the idea, and they didn't look at a lot of details, but I assume that they'll soon follow up with another paper. Is this possible? Yes. I'm pretty sure they'll be able to work out the math so that it's compatible with observations. The problem I see coming is this. While naked singularities form under somewhat different conditions than black holes, overall the process is kind of similar. I suspect it'll be very difficult to come up with an explanation for what happened in the plasma in the early universe that creates a lot of primordial naked singularities, but not also a lot of primordial black holes. And since we've pretty much ruled out primordial black holes, that'll rule out the naked singularities along with that. Then again, that's really just a guess, and I'll have an eye on how this idea develops, so stay tuned. Thanks for listening. We'll be back next week.